Yeah, once upon a time in Slack, in our company Slack. My boss came to me, and yes, this slide was updated for COVID-19, so she's wearing a mask, that our BigQuery costs show that a lot of money is being spent on joining articles with their assets. And my reaction was, assets have a huge history as well as articles. We can't simply join the two Apache Kafka streams. Why did I react like this? We use Google BigQuery as our data warehouse to store all information about our platform and analyze it. As BigQuery has a pay-per-query volume scheme, it forces us to find efficient queries and data models. We feed data through Apache Kafka topics into BigQuery, so joining this data has to happen either before or inside of BigQuery. And both of the two are separated. So the topics are not within the same, and also the tables are not within, or that they are two separate tables. For historical reasons, you would normally not separate them, but they are separated. My name is Toby, and I'm a data engineer at Ricardo, an auctioning site comparable to eBay based in Switzerland, as already mentioned. And we sell secondhand and new articles. We have these articles online on our website. And since Switzerland is a multi-language country, we have French and Italian descriptions, sometimes English descriptions. So the platform stores language-specific information in assets, and the generic article information, like if it's used or new, is stored in articles. As we move from a centralized database-powered monolith to microservices, everything was available through HTTP APIs. This worked fine for programming a microservice against them, but it's overloading the APIs when you need all of the data and not only small parts of it. So when I was thinking about doing HTTP endpoint and API enrichment in Beam, that sounded like a lot of overhead. Especially when you think about that you have to program against different APIs that might react differently. So you need a little bit of extra code here and there. As I'm not an expert on the topic of stream enrichment, I spent some time reading the Beam documentation and blogs. There are two main options to enrich data with Apache Beam that emerged when I thought about this topic of combining articles with their assets. First, there's a possibility of having slowly updating side inputs. Here, the slide inputs are made available to the workers. The data has to be fed into the pipeline to be able to have the pipeline manage the state. With large data, that becomes a problem. So we have around 2 terabytes of data for assets, and we don't have that much memory, so I dismissed this idea. Second, we could just do calls against our APIs, a pattern that is explained well in the blog post on the Beam website by Kenneth Knowles. However, this approach means hammering the APIs that are themselves then going back to the main core database, which holds data for the last 20 years, basically. And this increases the load on it. We couldn't simply let that happen. Also, again, each API might behave a bit differently. So programming for each API individually would cause a lot of overhead. So none of the two options is cutting it for joining the two streams in this case. So this is our basic pipeline pattern. Each topic, articles, and assets is processed by its own Beam job, reading from Apache Kafka and writing to two BigQuery tables. Each article can have multiple assets linked with it. The two tables backing this can be joined on the article ID. The article itself and its assets, like an article description in German, for example, can be created once and updated many times subsequently. To find the description of an article that was online on December 1st, one has first to join the two tables, and then the assets have to be filtered by their timestamp to find the correct one that was online on that day. As you can see, this becomes very painful with the assets growing over time, as I always need to scan the whole of them with these constraints. Now let's introduce a fast key value lookup store to this scenario. Having a fast lookup store means no more calls to the APIs, so no more overloading, which is great. The key value-based lookup store would be queried by the pipeline and provide the necessary information. The next question were, the next questions were how to keep it updated and what kind of technology to use for it. In our first draft, we had two pipelines in mind. One taking care of filling the key value store, and the other one was just an enhanced version of our existing pipeline that you just saw, using this key value store to enrich articles and writing the result to BigQuery. However, as Luke Civic pointed out on the Beam user mailing list when I posted this idea, we can't enforce that the history is up to date as the two pipelines are running with their own lag, leaving us with inconsistent data. For example, when the asset stream is lagging behind, an article might be linked to an old description of it instead of the one that was actually online during that time. So I took a step back and looked how Google's reference architecture was using BigTable, which is a fast and big key value store, to enrich streaming data. This is described in a blog post by Reza from 2017 about streaming mode large lookup tables for data flow. What if we update the key value store with the assets that are streamed in first, and then query everything from it for that particular article ID within the same doIfAnd function? At this point, you might think, wait a minute, you promised us 3 pipelines in your abstract. Where are they? And I have to apologize to you. Since the abstract has been written, things have evolved. There's just one pipeline doing all the streaming work. We make use of a co-group by key to join articles with their assets, process them together, and have a consistent view on the history of the assets. But of course, there's also a second one, batch loading the history from BigQuery into the key value store. As the second one is rather boring and just basically one I/O followed by some windowing and then another I/O, I will focus on the streaming one on the left with the live data. The pipeline first reads both assets and articles from Apache Kafka and then windows the peak collections into slices of 30 seconds and some allowed lateness to make sure that the co-group by key can correctly join both streams, and in the end, the result is being written to BigQuery. You can see the code, which is in Java, on the right side here. You can see that most of these are pretty basic constructs. You should maybe know if you have a little bit familiarity with Beam. The real magic happens in the enrich function here. So since it comes after the windowing and after the by key, we have the promise from Beam that our data is arriving ordered by event time, and all assets for a given key, article ID in this case, are being handled on the same worker node. Then we first insert for an article ID all assets into the key value store, and then we do a get statement for that article ID to fetch the history for it. So we looked at different technologies to do this kind of thing. And the first that comes to mind when you run on GCP is obviously BigTable. The problem is that BigTable comes with a bigger price tag and is starting at a 3-node cluster in production. For smaller teams or companies, this can be a burden. So we looked at alternatives for this approach with similar features and tried Apache Cassandra, which is now pretty easy to deploy on Kubernetes thanks to the open source CAS operator from DataStax. CAS is written C-A-S-S, like Cassandra in short. Apache Cassandra, compared to batched RPC calls against APIs, allows us to scan for timeframes pretty quickly, plus cheap and fast per key value lookups. So this answers question 1 about the technology. But how can we keep Cassandra updated so we only enrich the data with the articles, we only enrich the articles with the correct assets? The key here is to use the right consistency level, at least local quorum, which means that if you have 3 nodes, at least 2 of them, so a quorum, have to respond with the right answer to not end up with inconsistencies, and using a compound primary key that allows you to get the data back ordered by event time after you inserted it. That means that you not only have article ID in your primary key, but you're also adding, since this is the reason why it's called compound, the timestamp, the event timestamp to it. So then you can get the data ordered back by event time. So this is the streaming pipeline as displayed in the Flink web interface when it's executing. We are now combining the power of 4 Apache technologies, reading the newest assets and articles from the Kafka topics, joining and processing them in an Apache Beam pipeline running on Apache Flink, of which web interface a screenshot is taken from, while updating and fetching the history from Apache Cassandra. Unfortunately, I would have loved to show you the live thing, but I'm afraid that with the presenting software, my computer would just burn down. So you have to live with the screenshot for now. So now I showed you one pipeline in the beginning that delivered inconsistent results and 2 working ones, a streaming and a batch one, and introduced you to Apache Cassandra, which can be leveraged as a fast key value lookup store that is pretty much scalable. So what is left? We haven't talked about optimizing the enrich function, the doFn, yet. So we placed here a component that usually takes nanoseconds with one that can take hundreds of milliseconds in the worst case, as we currently do not do caching or batching. Yet the throughput to Cassandra is good enough on one worker for our use case already, and it can be scaled and optimized. To give you some idea, so you have around 20 assets or more per article ID that come in, and we can process then after the join, what the pipeline drops out is about 70 to 100 articles per second, which is for one CPU core and one worker pretty enough for us. And then it can be accordingly scaled, of course, adding more workers. Even though we haven't optimized this code yet, so adding caching inside and doing proper batching will further increase this. Of course, adding a component like Apache Cassandra significantly increases the load on operations. After the proof that our prototype works, which I hope I did with this, but let's see, we'll have to compare the costs to something like BigTable, which is a managed database basically doing the same thing, or other technologies. We believe the approach should work for BigTable too, as BigTable offers read your write consistency. So that means that when a worker inserts new assets for an article ID and subsequently reads assets for that article ID, the worker will always see its own writes. So we will never see stuff that it always catches its own updates. And since the co-group by key makes sure that everything is being processed per worker on one worker, we can be sure that we will always have consistent data, even with only read your writes consistency. We also are looking forward to update Cassandra IO in Beam to version 4.x, currently is 3.8, to benefit from better timestamp support and basically removing all the custom code we have to go from Cassandra's CQL, which is Cassandra query language, timestamp types to Java time instant. This all has been improved in the 4.x version. I think right now it's 4.8. But it would mean a little bit of work in the Cassandra IO component. We also look forward a lot to the improved schema support in Beam. So this would make this use case even better and even easier, because right now we do a little bit of manual work with protobufs. And with that, I want to say a very special thanks to the Beam user mailing list, especially to everybody who responded on my thread. And I want to leave you with this references slide, which actually tells you where you can find more information about everything that I just talked about and where I got the information from. And I also linked here the DataStax CAS operator for Kubernetes. I invite you to join, which is on this Slack, actually. On the Beam Slack, there's also the Cassandra Slack, and they have the CAS operator there too. So it's pretty new yet. It's, I would say, production ready, but it's still a bit bleeding edge. But the point of this is always trying new things. So that was my main point here. And I have to mention that, I want to mention that we are, if you like what you heard and enjoy working with exciting new technologies, why not join the data intelligence team at Ricardo as a technical data analyst? So you will join my team and work on stuff like Beam or deploying machine learning models to production. And now the only thing left to say is I want to thank the organizers for organizing this online summit. So it's really nice. It's really nicely done, especially the gathering space and the space to talk to people. So yesterday evening we had a lot of fun walking around in this virtual world. Since now I have 5 minutes left for questions, as planned, I would like to hear your thoughts on this. So have you ever encountered the issue that you wanted to join two streams or you wanted to look up something and the state didn't fit into the workers? What are your thoughts on this? And also, did you have different approaches to solving this problem where you couldn't store the state on the workers themselves? If you have any questions, just ask them. I'm happy to answer, and I'm also around the whole summit. Thank you for your time, and again, thanks to the organizers.
Thank you very much for those kind words, Toby. Thank you for joining. Thank you for sharing your journey, as well as sharing those resources. I'm sure they will be super useful to a lot of the people out there. We actually have a few questions from the audience already. So if you're happy with that, I'll just go ahead and shoot. So the first one is: was memory store considered for a key value store, assuming you're running this on GCP?
Yes, we have memory store in usage. I was actually considering it. But if you open the cost exploration for memory store and you look up how many, like for example, if you want to store things like 1 terabyte or something like that in memory and compare that to a Cassandra cluster open source on GKE, then GKE wins. So that was also a cost consideration, but absolutely correct. You can do this with memory store, which is easier, I would say. But then you at some point hit the wall when you use Redis, at least that if the instances don't have enough memory anymore, you are out of luck. And yeah.
Cool. Yeah, I think that makes a lot of sense. And then there's a second question, actually. Someone is asking if you would elaborate a bit more on the choice of the runner as well.
Why were you okay? So the Flink runner was chosen because we were running on the Flink runner already. So we had some experience with it. And what we also knew was that connecting from that, because Flink cluster works in a dev cluster that we control in Kubernetes in our own GKE cluster we spin up for this. You don't have any connection issues. So if you work in a company where people and teams are split and there are different GCP projects, and then, for example, there's the engineering GKE cluster, and then there's your team's GKE cluster, you have to bridge them somehow. They have to talk to each other. And if you run your Flink cluster inside of GKE and you have Cassandra inside of GKE, they just talk to each other. So that is for development a huge plus. Obviously, if you would run the data flow stuff then in the same project again and you would link it to your GKE cluster, that would also work because they have the same networks and you can share the same IPs. But historically, again, this is a bit scattered with different projects. So we have the Flink runner was just the first choice, also because you can overload the Flink runner. So you can say that a Flink worker offers 4 slots, even though he only has 2 CPUs, where usually you would only assign 1 slot per 1 CPU. So it allows you to under provision, basically overcommit for some resources, and that is quite useful if you want to squeeze out the last bits of performance versus money.
Yeah, that makes a lot of sense as well. Nice. There's one more. I see we're going a bit over time, but we have a break after this. So if you're happy to take
I'm
another.
fine.
Okay, cool. Have you considered using Flink's RocksDB state backend to work around the state
Very
side?
good question. Very good question. Absolutely, yes. And then there was this thinking of, yeah. So there, how to put this? So I'm trying to learn one new technology at a time. And the thing is with Cassandra, we knew that Beam is working, Flink is working. We only need to adjust it to Cassandra. RocksDB was on the menu. Again, RocksDB is somehow managed inside of Flink, and accessing it with the new version 1.10 and so on became easier. So Flink now allows you to access the state. So it was on the list of things we thought about, but the problem is just that you are basically doing something which the thing is not really intended to do. So it's like building a motor, putting an electric motor next to an existing engine in a car, basically a combustion engine. It will work probably if you make it right and you have a good mechanic. But it's definitely not the standard way, let's put it this way, to do it and operate it. And since we have limited resources available to then look after the thing, we were not sure if our pipeline was wrong or our approach was wrong, or maybe we overcommitted RocksDB, or we would need to give it more memory and then get another node pool with more memory for it. So we try to then limit the amount of new stuff basically trying out. But it's definitely something to look into, especially when the latency in RocksDB will be much better than in Cassandra. Absolutely. That's being said, just one more thing. So I did a test, and for the writes, it's 0.0, so it's sub-millisecond. I think it's 30 nanoseconds or something, or 50 nanoseconds for the writes for Cassandra right now. So that's pretty good already. The reads are 1 millisecond, but that's just because we have to do 2 lookups right now because the data architecture is not perfect. But yeah, so we're pretty happy with the performance. But yes, this is also something that could be tried.
Awesome. I think this was very helpful for the people in the audience. A lot of knowledge there, definitely.